Hello everyone. I'm Shubham and I work for a smart metering company called Discovergy, and we are based out of Germany. So today I'm going to talk about how we can get uncertainty estimates from deep learning models for non-intrusive load monitoring. But before that, I'll just give you an overview of NILM at Discovergy. So we use like three-phase electricity data at 1 to 2 second resolution from our smart meters. We use deep learning models wherein we train appliance-specific classifiers and identify 7 different appliance categories. And once we have done the disaggregation, we show the results to our users using a web portal and a mobile app, along with some of the consumption statistics from the history. So just an overview of our approach here. As we said that we use an input window of the aggregate data, and we train an appliance level classifier to predict 3 things. One is the start time, the end time, and the mean power of the appliance during that window. We use convolutional layers heavily in our network, and networks are usually 15 to 20 layers deep. So this is how it looks like on the dashboard. We have the 3-phase data here, and after disaggregation, it looks like this, wherein you can see these boxes, which denotes when a particular appliance started and how much power they consumed. So we have been showing disaggregation to our users and providing the service to them. But the big question is that how good we are doing. One way that people test this is you run your algorithm on a test data set, calculate the error, and hope that this error resembles the error you would get in a real world setting. But we're not sure if that makes sense, because a lot of times in real world, you have much more complex data streams, and there could be domain shifts in the data, and you need to be sure if you're making right predictions. So we wanted to answer these questions and see if it's possible for us to identify possibly wrong predictions without knowing the ground truth in the first place. And even if we go out and collect ground truth data from our users, for example, asking them to confirm some predictions, then we want to do this intelligently. We don't want to nag them for every prediction, because it can get cumbersome. So the problem here is that from deep learning models, you only get point estimates, especially in a regression setting that we used. And there's no clear way to obtain uncertainty estimates or confidence intervals of our predictions. So the option with us was either we go to using Bayesian methods that have been studied a lot for NILM as well, and try to get uncertainty estimates from there. But we saw that our deep neural networks were performing very well for disaggregation. And we were trying to see if we can combine the 2 methods. A lot has been done in the literature already to combine these 2 things in the form of Bayesian neural networks. And the key idea there is that instead of having deterministic parameters for the network, we have a distribution over the network parameters. So the way this works is you place a prior distribution over the network parameters, and then try to estimate the posterior distribution given the data. Once you have the posterior distribution, you can just do the inference by marginalizing over all the possible parameter weights. But the tricky part here is, as was also mentioned in one of the earlier talks, it's very hard to calculate this posterior because of the denominator here. We have to integrate over all the possible parameter combinations, and this integral becomes intractable. So this is like one of the main problems, one of the central problems in Bayesian learning, and it has been studied very well. And people have developed very good approximations to solve this. One of the methods is called variational inference, wherein instead of trying to estimate the posterior, you assume an approximate distribution and try to make it as close as possible to the posterior distribution. So we could have done that, but the problem with this is that we cannot use our already trained models, and we have to change our training regime. And we were trying to see if we can do something with our existing models and obtain it. So Yarengal and Gheramani had an interesting insight. They proposed a method called Monte Carlo dropout method, wherein they proposed that training any neural network with a dropout is equivalent to training a Bayesian neural network. And so the way this works is that for any input xi, if you do n forward passes and obtain the prediction from them, then you can just get the predictive mean and the variance from these predictions. So this is like drawing Monte Carlo samples from the distribution without actually having to calculate the posterior. So I won't go into the maths here. You can go through the references to check out the math. It's quite interesting. So we wanted to see how well this works for NILM, and we set up few experiments to investigate that. The setup is as follows. We only show results here for a washing machine, and we have like 27,000 examples in the set that we're using. It's a validation set. Out of these 27,000, 9,000 had a washing machine running in them. And we used one of our previously trained convolutional network for these experiments. We conducted 50 forward passes for each input to calculate the mean and the variance. So what we have plotted here is a histogram of all the uncertainties that were calculated from the Monte Carlo dropout method. And what we see here is that there's a high uncertainty for input windows where the appliance is active. This seems quite obvious because it's usually easier to say if an appliance was not present in the window, because you just need to look for coarse features, where it's super hard to actually predict the correct time and the energy. Now, I'm sure you all recognize that this is a washing machine. Not every conference you can say that. And what we do here is we increase the complexity of the input window. So from first to third, you can see that there's already a lot of other overlapping appliance signatures here, and it becomes difficult to identify. What we see here is that the variance also increases for these examples as the complexity increases. So this tends to show that the variance is an indicator of the complexity of the input image that we are trying to predict for. To answer our question, is it possible to estimate the prediction error without actually having the ground truth? We wanted to see if uncertainty can be used there. So in this example, you'll see that, so the green one is the prediction box that we obtained from the neural network, and the orange one is the ground truth box. And you see that it does a good job at predicting this. The mean squared error here is super low, and so is the variance. Whereas in this case, where the prediction is not so good, you also get a super high variance. This confirms the intuition that probably we could use variance as an indicator for the error. However, we go a bit deeper into this, and we plot we plot all the uncertainties again for those instances where a washing machine was detected. And what we see here is that in cases where there was a false prediction, you get much higher uncertainties as compared to the one where the prediction was correct. So in absence of ground truth, high predictive variance can indicate false predictions. We ran another experiment wherein we calculated uncertainty for all the examples and sorted them by increasing order of variance. And the idea here was that higher variance examples are probably wrong. And so if we can eliminate them, the rest of the data set, the error on rest of the data set will be lower. So what we do here is that gradually we increase the tolerated variance, which means in a way that we increase the number of examples where the error might be high. And you would expect that the mean squared error would increase. This is what we observe again here. So it in fact increases almost monotonically with the increased variance. So this seems promising, but the question was that are these estimates calibrated? Because if they're not calibrated, we can again start making errors. To test that empirically, now you would assume that if you have a 90% confidence interval around a prediction, you would expect the values to lie around 90% of the time within that interval, right? So at least in the frequentist interpretation, right? So what we did here was we obtained estimates by MC dropout and plotted the number of times each value, number of times the predictions lied within the confidence interval. So for example, here for 80% expected confidence interval, you would expect that 80% of the time the predictions were within the confidence interval. However, we see that that is not the case, and there is some gap here, which shows that the estimates might not be calibrated. To circumvent this problem, and still be able to use uncertainty obtained from this method. What we instead do is we use percentile scores, wherein we rank the uncertainty obtained from a new prediction with respect to the already existing data set or the population, and then assign a percentile score. So basically, higher the percentile, higher is the uncertainty, and probably that needs to be checked further. This is a bit distorted here. So the schema that we came up with was that once you make a prediction and estimate the variance, if an appliance was detected by the network, and if its variances percentile score is higher than a certain threshold, then we can either prompt the user to ask for a confirmation and show, hey, probably this was a washing machine, can you confirm? Or we can refer it to a secondary system, or at least like ask our experts to check what is going wrong here. So at least we know where we are missing out. And this can further be used to improve the model. To test this scheme, we ran a small experiment wherein we collected all the examples. So I'll just first explain you the control experiment. So what we do here is we randomly pick a certain fraction of the data examples out of the sample set and calculate the error on the remaining one. So for example, here only 20% of the data is retained and the rest has been pulled out. This is done randomly, so you get these mean squared errors. And to check our experiment, what we did was we now select data points which had very high variance, so that we can eliminate those predictions where we are probably making the most mistakes, and calculating the error on the remaining set. What we see here is that the mean square error is like super low as compared to the random case, and it only increases once we retain the entire data set, meaning we retained like all the points wherein the network was making wrong predictions. So this seems to suggest that if least certain points are referred for further review or further inspection, the performance of the NILM model can be increased. We'll try to see how we can use this to like retrain the model and provide this feedback, but that's for the future work. Thank you, and happy to take your questions.